Hello everyone and welcome back to another video. May the 4th be with you today. And what we have above at the top of the screen is a relationship between the eta function and the zeta function, which was conjectured originally by Euler. And my goal for this video today is really just to prove this right here using Riemann's functional equation, the Euler's reflection formula, and as well as something we proved, I think a couple of videos back. So, to get started, what I'm going to do is essentially consider eta of 2n, which is just equal to, if we put this in series form, the sum from k, oh my goodness, I can't write a k, the sum from k equals 1 to infinity of negative 1 to the k minus 1 over k to the 2n. And one thing that we can do with this to exploit a bit of symmetry, noting this 2 here and essentially assuming that n is some sort of integer, one thing that we can note here is that this is the same thing then, as a result of symmetry again, as 1/2 times the sum of negative 1 to the k minus 1 over k to the 2n. So this part hasn't changed, but our bounds for the summation have changed, and they're from negative infinity to infinity. And the reason that I've done this is essentially so that we can apply one of the results of complex analysis here. And that is namely that the sum from k equals negative infinity to infinity of negative 1 to the k times f of some k is equal to the negative sum of the residues of pi times the cosecant of pi x times f of x. And these residues are just at the poles of f. And one thing you might note is that we can almost but not quite, apply this equation right here from complex analysis to our equation right there. But just one thing I'd want to do first is multiply both sides by negative 1, so that way we get a positive here, and then a negative up there, so that way we can just directly substitute in our f of x. So to evaluate this series, we can actually just simply find the residues of pi, so I'll write this out. So what we're going to be finding the residues of is going to be pi times the cosecant of pi x. But then our f of x is just going to be, well, just 1 over k to the 2n, because that's what we have there. So over k to the 2n. And we need to find the poles of f, but that's actually quite simple, because the only place where 1 over k to the 2n could possibly be, well, undefined is 0. So we just need to find the residue of this at 0. So I'm going to scroll down now. So what we can do now is really just apply, well, the definition of a residue. And I'm going to write out the entire formula for once. So yes, what we're going to do is, actually I'm going to rewrite this first slightly differently. I'm going to say this is pi over the sine of pi x times k to the 2n, because I actually don't like cosecant, and also this makes what I'm about to say a bit more clear. So one thing that we have to essentially find is the degree of the pole at k equals 0. And initially you might say, oh, it's, the degree is going to be 2n, but that's not entirely true, because we have the sine of x right here. So really the degree of the pole is going to be 2n plus 1. Because, again, sine of 0 is just 0, so that contributes to the degree of our pole as well. Meaning that according to the residue theorem, we have our derivative with respect to, well, oh, geez. I'm really getting this notation mixed up. This should actually be an x here. I do apologize. Boop. Boop. Okay. D over dx, and the degree, we're going to differentiate, however, we're going to differentiate the degree of our pole minus 1 times, so that's going to be 2n times. So if the 2nth derivative of pi over x to the 2n times sine of pi x but then times x to the degree of our pole, so 2n plus 1. And on the outside, what we have is the usual 1 over the degree of our pole minus 1 factorial. So that's just going to be 2n factorial. And this is going to be the limit as x approaches 0. But one thing to note is that we are currently finding the residues for this series right here. But this series is actually just 1/2 of what we actually want to be evaluating, which is our zeta. So what I'm going to do is just say this is 1/2 of all that, and then just set zeta of r to n equal to that. So let's get evaluating, shall we? This looks not so nice, but it does simplify at least a little bit to begin with. So we are going to have 1/2 times the limit as x approaches 0 of 1 over 2n factorial. The parentheses should be the other side of the factorial. And then we have the 2nth derivative of pi x over sine of pi x. And this right here looks quite daunting to evaluate, but thankfully, in a previous video, which you should definitely check out, shameless plug, but we did evaluate this nth derivative in another video. And the reason I'm not going to be proving it here is because it did take me 15 minutes. So in order for this video not to be 30 or 40 minutes long, I'm just going to simply, I'm just going to tell you what this is. This right here, at least in terms of the zeta function, it's just equal to, it's quite long, but it's equal to 4n times pi to the 2n times -1 to the n plus 1 times 1 minus 2 to the 2n minus 1 times zeta of 1 minus 2n, which is quite a mouthful. So subbing all of this in, and since I don't feel like writing that whole thing again, I'm just going to add this out front. So we have a 1 over 2 times 2n factorial here, and then that's just equal there. And the limit is already taken care of with this right here as well. And as such, what we can find with this is once we apply Riemann's functional equation, this simplifies quite a bit. But this is actually what I was staring at for quite a while last night. But again, as soon as we apply the functional equation, which is, I should write out by now, which is zeta of s, of just some s, is equal to 2 to the s times pi to the s minus 1 times the sine of pi s over 2 times gamma of 1 minus s, and then times zeta of 1 minus s. Which again is quite long and not very nice, but if we simply let s equal, say, 2n, then what we find is that this becomes, or perhaps I should solve for zeta of 1 minus 2s, 1 minus 2n first. That would be more helpful. So zeta of 1 minus 2n, we just got to move all that to the other side. So I'm just going to write the zeta on the numerator, so zeta of some 2n, over 2 to the 2n times pi to the 2n minus 1 times the sine of pi s times gamma of 1 minus 2, 1 minus 2n. Which looks quite messy, especially once we combine it with this. But you'll notice that some things actually do start to cancel out. So I'm just going to zoom out quite a bit and essentially sub that in. Whew. This is quite a lot, but we are making progress. What we have now is our zeta, our eta of 2n is equal to 1 over, actually I'm going to write it like this. We have our 4n pi, I'm going to drop the parentheses actually, 4n pi to the 2n negative 1 to the n plus 1 times 1 minus 2 to the 2n minus 1. There should be a minus there. I do apologize. Didn't want to write. Times zeta of 1 minus 2n. Or sorry, not zeta of 1 minus 2n. Zeta of 2n, because we are subbing that in, over 2 times 2n factorial, and then the rest of this nasty denominator, times 2 to the 2n, pi to the 2n minus 1, times the sine of pi n, times gamma of 1 minus 2n. And all of this looks extremely messy, but you will see that some things start to cancel. I sound like a broken record right now, but I swear they actually do. The first thing that you'll notice is actually these pi's to the 2n do cancel, meaning that we're left with just a pi on the numerator. And also that we have this 4n right here. But we're dividing by 2, so essentially we have a 2n on the numerator. But you will also note that we have a 2n factorial on the denominator. And since we have a 2n over 2n factorial, we can just, this is just the same thing as 1 over 2n minus 1 factorial, which is just the same thing as 1 over gamma of 2n. And the reason I'm writing that in terms of the gamma function is because we have a gamma right there. So just getting everything in terms of that, we can apply, well, I'm jumping ahead, but we can apply Euler's reflection identity. That's all a lot, so I'm just going to rewrite all of this real quick. What we have then is our fraction bar, gamma of 2n times gamma of 1 minus 2n times the sine of pi n, and then I'm going to put this 2 actually up in the parentheses with the other 2. So what we have is a 2 to the minus 2n minus 1/2. And we still have that negative 1 to the n plus 1 and our zeta of 2n. And I believe that should be everything. The hardest part about this really is just keeping track of all your terms because there are so many. But I do believe... Oh, apologies, there's a pi. Yes, there's a pi right there. Okay. So, now that we've kept track of all of our terms, what we can do now essentially is apply Euler's reflection identity. And that right there, if you do permit me to change colors again, is gamma of 1 minus some s times gamma of s is equal to pi over sine of pi s. In this case, our s is just going to be 2n, as before, meaning that our gamma of 2n times gamma of 1 minus 2n is going to be the same thing as pi over sine of 2 pi s, but it's 1 over that. So really it's going to be sine of, sorry, not pi s, 2 pi s, 2 pi s over pi. So subbing that in real fast, what we find is that this simplifies a bit to 2 to the minus, actually I'm going to add in, I'll multiply the top and bottom by 2 real fast, just to get rid of that 1/2, so we have a 2. I mean, also for other reasons, but I'm not going to explain those. All right, now 2 to the 1 minus 2n minus 1 times negative 1 to the n plus 1 times zeta of 2n, and then the pi's are going to cancel, leaving us with a sine of 2 pi n, should be an n, 2 pi n, and then a sine of pi n on the denominator. And one thing we're going to do next is just apply the, I always forget the name of this identity, but the identity that sine of 2 theta is equal to 2 sine theta cos theta. We're just going to apply this here, that way we can get this and this to cancel. And what this leaves us with is our 2 to the 1 minus 2n minus 1 times negative 1 to the n plus 1 zeta of 2n. And then our signs are just going to cancel because, I do apologize, there's a 2 there. Our signs are actually just going to cancel, leaving us with cosine, and this 2 is going to cancel with that 2. So what we have then is a cosine of pi n right here. And let's think about what cosine of pi n actually is. So if we plug in 0, we're going to get 1, but if we plug in 1, we're going to get cosine of pi, which is negative 1. If we plug in 2, that's going to be cosine 2 pi, which is just 1. So what this is essentially is just a negative 1 to the n. That's what that is right there. Meaning that we can cancel this cosine with most of that negative 1 to the n plus 1. We're just going to have an extra minus sign out front. And as such, what we find is that we have negative 2 to the 1 minus 2n minus 1 times zeta of 2n. But we can just distribute the negative sign, and what we find is that this is just equal to 1 minus 2 to the 1 minus 2n times zeta of 2n. And what we said at the very beginning of this was that this was equal to eta of 2n. But you'll notice that all of these are 2n right here. So if we simply let, 2n be equal to, say, s, what we find is our original, or Euler's original conjecture, and that is eta of s is equal to 1 minus 2 to the 1 minus s times zeta of s. And there we go. We have successfully proved, with many identities and a lot of not so nice algebra, Euler's conjecture. So thank you all for watching today. This was a kind of long and messy video. I do apologize for that, but I still hope all of y'all enjoyed, and I will see you in the next one.